Um, so I looked over those of you that had topics. There's still a few that haven't picked a topic. And I think I just talked to the two of you that I had some questions about your topics being a little broad. If you have some more questions about that, I'd be happy to sit down with you individually and kind of flesh things out. I will probably, over the next couple of days, put together a schedule, a tentative schedule of what days we're going to do it and who's going to present and things like that, at what day. And again, you're welcome to come to all of them. I'd like you to come to half, but I'm not going to require that you come to all 6 or 7 days of presentations unless you want to. You're welcome to. You may find that they're more interesting than the lectures. I find they're more interesting than the lectures. I've heard the lectures before. Yes? It's going to be towards the end of October, beginning of November. And it'll be spread out over a couple of weeks, okay? And I might try to pick different days, like some Tuesdays and some Mondays, because some people have scheduling things. Although I think we've solved most of the scheduling problems with the 8:30, 9:30 slot. But in any case, so we were talking about aluminum. Any other questions? Okay. We were talking about aluminum, and I just want to finish up a little bit with give you some idea of the scale of aluminum production and compare it and contrast it with steel, which is 40 times the scale in terms of amount of material made. But also I want to talk about some of the corrosion or fatigue problems. Anybody know what this is a picture of? Aloha Airlines, okay. This was 25 years ago now. It was a while ago. But this was, I think, a 737. And it was basically flying on not chartered, but on scheduled flights between islands in Hawaii. And it never went, except for being flown out to Hawaii, it was always just doing these 20-minute flights from island to island, okay? And so as a result, it had like 100,000 cycles or 60,000 cycles in about half the time of a regular aircraft, because its flights were an average of 20 minutes or 30 minutes as opposed to 45 minutes or an hour, because the islands are so close together. It turns out the fuselage of an aircraft, a pressurized aircraft, is a pressure vessel. You've got higher pressure inside than you do outside. It might be 8/10 of an atmosphere, so it's like being in Denver at a higher altitude. But outside, it might be 4/10 of an atmosphere. I don't remember what it is at 40,000 feet, but there's a pressure differential, and so you actually have to build this thing as a pressure vessel. And every cycle, we call gag cycles, ground, air, ground, taking off and landing, you pressurize it and depressurize it. That's a fatigue cycle. So this thing had 40-some thousand cycles, and finally, it just let go at all the rivet holes, and the whole top came off. Only one person died. There was a stewardess who was not sitting down and seat belted in. The people who were sitting in a seat and had seat belts didn't get pulled out. She got pulled out and perished, but the thing landed, yes. Okay. Yeah. Yeah. Yeah, this was, as I remember, this was around 60,000 cycles, but it was like 40,000 hours or something. It was a lot fewer hours. And this is what happens in corrosion or fatigue. Whoever's the leader is going to be the first one who fails. I'm going to give you another example. But this happens to be a fatigue failure. It was partly corrosion fatigue, so far as that goes. I was amazed until I stopped to think about it. There really is a keel beam down here. I always thought if you lost over half your pressure vessel, the whole thing would just crack up. But in fact, it's got this great big I-beam down here made out of aluminum. And so, you know, it's just sort of a pressure vessel canopy, if you will, so far as that goes. But so aluminum we have to worry about some of the lifetime problems. Another example I have here is this washer, which it's got a gray edge, which means it came from a Seahawk helicopter. This is a steel nut that goes on top of it, and the holes don't line up because it's designed, instead of having a cotter pin or something, you put the washer on and you put the nut on and you tighten it to the proper torque, and there's one more hole in one of these than in the other, and so there'll always be one that lines up, and you put a screw through it to keep it in place rather than a lock nut or a lock wire or a washer or something. And this essentially holds the tail rotor of a Black Hawk helicopter or a Seahawk helicopter. And like I say, one's an Army part, one's a Navy part. I don't have a lot of these, but in fact what had happened is this particular alloy was 6061, which I told you was the workhorse aluminum alloy yesterday, and it was supposed to be 6061 T6 heat treatment, which is solutionized and artificially aged, and it was supposed to be a 5-1. 5-1 means they would take the bar and they'd stretch it 1% to relieve residual stresses. This is made from I don't know, like a 3-inch bar and machined into a washer. And when they bought it from Alcoa or whomever, they would, when they make the bar, they would heat treat it to the T6 condition, but in aluminum, because of the good thermal conductivity, the quenching process introduces residual stresses. And the 5-1 is a way to relieve residual stresses. Now this tensile relief of residual stresses by mechanical means is common in a lot of aluminum alloys. I mean, they will take whole plates. At the Davenport, Iowa, world's largest rolling mill, is not for steel, it's for aluminum. And in Davenport, Iowa, they have this kind of 12-foot wide about, I've only been there once, but anyway, about 12-foot wide rolls with 4-foot diameter steel rolls to roll the world's largest steel plates. And what do we use the world's largest steel plates for? The world's largest aircraft wings, okay? All the aircraft wings, you know, for Boeing and not necessarily for Airbus, they may get theirs from somewhere else, but anyway, for Boeing or when McDonnell Douglas was in business, they all came out of the Alcoa Davenport works. And there are residual stresses, and they will take these huge plates that are 4 inches thick, and I've been to the room where they have these big hydraulic expanders, and they just grab the plates, which might be 30 feet long or something, and they just pull them 1 to 3% in plastic strain to relieve the residual stresses from heat treatment. And that's because the residual stresses from heat treatment can lead to stress corrosion cracking, which is exactly what happened to the washer. Actually, it was on an Army helicopter, Sikorsky Black Hawk, but it cracked. They lost the tail rotor. It wouldn't spin because it no longer had the tension on it it was supposed to have, holding it together, and it's just sort of freewheeling. And the helicopter started spinning around and crashed and killed a bunch of soldiers in Arkansas. So anyway, they started looking around saying, well, why did this happen? And it turns out Sikorsky says, oh, we shouldn't have been using the T6 heat treatment. We should have been using the T73 heat treatment. And T73 is a heat treatment. This is aged for optimum strength. This is actually overaged. You go past the peak strength and you get about 10% lower strength. If you look at the tempering curves for aluminum, they'll kind of go like this. This is time versus temperature. And if you actually, this is optimum age, that's T6, and T73 is the temper that's just passed by about 10%. But the toughness like doubles, okay? And the stress corrosion cracking resistance increases by about a factor of 2 on stress, which is like a factor of 10 on life in terms of corrosion fatigue. So they had actually had this problem in a different helicopter, not the Black Hawk or the Seahawk if it's a Navy, or it's the Jayhawk if it's the Air Force, the Coast Guard, or I can't remember what the Air Force. It's all, they make the same helicopter, basically the same helicopter for all the different services, but they have their own name for it. There's also another form of the Black Hawk, which is called the presidential helicopter. And if you go down to Sikorsky, where they make that version is in a super secure area, and it has all kinds of super secret stuff on it, and communications gear and stuff. Well, it turns out the washer is exactly the same. And what had happened is they investigate this failure that killed a few people in Arkansas, and they said, oh, this other helicopter group had seen this problem, and they had switched from T6 to T73 to get to double the strength of stress corrosion cracking in the aluminum alloy by going to the overage condition. And so Sikorsky said, oh, well, we better order some new washers of T73 that won't stress corrosion crack, because they started looking and they found these things sitting on the shelf in Navy supply depots with cracks, stress corrosion cracks in them. Never been put in service. Just the residual stresses from the original manufacturer were about, we measured them, that's why it's got a little cut in it, but we put some strain gauges, or actually we didn't take strain gauges, we just measured the distance between these flats before and after cutting, and then estimated the residual stresses as 8 KSI. Turns out 5 KSI is the stress corrosion cracking limit. So this was, the residual stresses were enough to crack this thing on the shelf without ever putting it in service. The Navy saw it first. Why? Because the Navy is the corrosion leader in the military. They put everything they've got and surround it by salt water, okay? And so the Navy will crack things first. Anyway, the Navy had seen some. The Black Hawk design team kind of went and found out from this other design team, oh yeah, we switched those over to T73. So they order 1,500 of them, 15-month lead time. In the meantime, the helicopter goes down in Arkansas, okay? But fortunately, it wasn't the presidential helicopter, although it depends on whether you're a Democrat or Republican at the time, okay? Aluminum in general has very good corrosion resistance as pure aluminum. That picture of the Aloha Airlines, the outside skin is a clad aluminum. For 60, 70 years, we've been making roll bonded aluminum, where you take a heat treatable aluminum plate, 2024 typically. In fact, when I had that FAA manual, the old Mill Handbook 5, I opened it up, it was 2014 Alclad. They call it aluminum clad. It's aluminum clad aluminum, and I'll explain what this is in a second. And they've been using it for 70 years. They basically roll a pure aluminum, 1100 aluminum, and roll it into about 1-inch thick plate. They take an ingot of like 2014 or 2024 heat treatable alloy. They roll bond that 1-inch thick pure aluminum on the surface of the heat treatable aluminum. The pure aluminum has no copper, so it doesn't set up little galvanic cells that can lead to corrosion between the aluminum and the copper precipitates. So the 1100 aluminum is fantastic in corrosion resistance. We use it for things like cookware in the kitchen. Okay, not much strength, but if all you're doing is lining the bottom of a pan to give it good thermal conductivity, and it's a stainless steel pan, you just want good thermal conductivity, but you want good corrosion resistance. You don't want it to pit and things like that. You use pure aluminum. Well, that's what they started doing with the skin of aircraft. Aircraft are very expensive, so they learned to roll bond a very thin layer. So if you had end up rolling this big ingot that had clad surfaces of aluminum, you might roll it down to 1/16 of an inch thick, and it'd have 1 or 2 thousandths of pure aluminum on the surface, called Alclad, aluminum clad aluminum. A couple of years ago, a guy in Spokane, Washington, whose father and uncle had invented the process or the machinery for casting essentially all the aluminum in the world, developed a process to jointly cast one aluminum alloy next to another aluminum alloy, and so instead of roll bonding this, they could cast continuously, and this would be the 1100 aluminum, and this would be the alloy aluminum over here, etched a little different color. And this is actually a casting fusion line where they cast it in shape, and so they no longer had to roll bond, and made clad type of aluminum sheet much, much cheaper. And that's kind of coming to the market and bringing aluminum into lots of things like kitchen appliances and other things, where it didn't have as kitchen appliances being like stoves and refrigerators and stuff, where it didn't have as big a market, because you can now have a corrosion resistant surface with a high strength core. Essentially it's a composite that they grew from the melt. So they reduced the price of this aluminum composite dramatically, and that was about 5 or 7 years ago that came on the market. Nope. It's a continuous casting process, and they pour the molten aluminum in here, one alloy, and they pour the other aluminum in here. And it turns out for aluminum, it works that the two of them just fuse together. This is actually a fairly broad fusion line. Okay. Let it focus there a little bit. I mean, you can see it's a millimeter wide. And if you got it in there, you'd see a fair amount of mixing. Okay. But they just cast together. And now it's the whole aluminum casting process is called direct chill. You start off with a water-cooled copper plate about the size of a desk, which is going to be the size of your ingot, and some water-cooled copper molds, and the bottom of that mold will withdraw, and you basically just pour aluminum in. It freezes on the bottom, it freezes on the water-cooled sides. It's called DC casting, direct chill casting of aluminum. And you withdraw that thing, and you make an ingot that's 20, 40 feet long by 5 or 6 feet wide by 2 feet high. But now you can make it with 1 or 2 clad layers, or actually you can have up to, well, they've done up to double layers of cladding. You may want to have a brazed alloy in there, okay? And it's not always you want corrosion resistance. Sometimes you want a brazed alloy. All the aluminum that goes into automotive radiators is brazed. And so there's a tremendous volume of radiator sheet so far as that goes. In any case, you got to worry about some of the corrosion resistance of aluminum. Since one of you is interested in sailing, I brought one of my America's Cup projects. I don't know if you can see it much anymore. It was always hard to see. I never have etched it. Anyway, this is a fractured hydraulic cylinder from America's Cup. Okay, the fracture origin is right here, but over time it's hard to see it unless I put it in a microscope. It's right there. Okay, but the America's Cup is sort of interesting. In most cases, we don't want things to fail, and we don't want them to fail for a long period of time. The America's Cup doesn't last that long. And they say, their philosophy, I've talked to one of the guys who used to be a graduate of mechanical engineering here at MIT, who makes components like this, and he brought this to me once. He's down in Connecticut, has a company called Navtech, and they make high-end marine equipment, hydraulic cylinders and things like that. So that makes one-of-a-kind, special-purpose things for people like the America's Cup. But stainless steel turnbuckles and aluminum cylinders. This is a 7,500 psi hydraulic system for raising and lowering the sails. And 7,500 psi, if you know anything about hydraulics, is pretty high pressure. Okay, the Black Hawk helicopter went to 3,000 psi hydraulics to save weight, but they didn't go anywhere close to 7,500. So they're not the V-22 Osprey went to 3,000. Typical hydraulic might be 1,500 or 2,000 in most equipment. But when you get really weight critical, they will go to, rather than steel hydraulic cylinders, they'll go to aluminum, and they'll make them so thin that they expect them to fail. In fact, what he told me is if they don't fail, then you're making them too heavy in the America's Cup trade. Okay? You don't want them to fail. You want them to last as long as a race, but they don't care. I mean, they're spending $100 million on these vessels, and you know, you've got a multi-billionaire who wants to have bragging rights at the yacht club. Okay, that he, you know, funded the America's Cup, and so he doesn't care if it fails, and he has to spend another $5,000 for a silly little hydraulic cylinder. But you do want them to fail safely, okay? And the problem was these things were exploding when they failed. And it was a little stress corrosion fatigue crack starting from the outside. And he brought me this thing and wanted to know, what do we do about it? Well, it turns out, I think it was 7075 T6. Here are my notes from the letter he sent me originally. Yeah, it was 7075, which is an aluminum zinc alloy. So erase that and put in 7075. And it was stress corrosion cracking. They had gone to T6. I don't think they had the 5-1 heat treatment in there necessarily, the stretching. But in fact, the solution to his problem was, that was like only 1/8 of an inch thick, to go from 3 millimeters thick to 4 millimeters thick, to increase the wall a little bit, because we're going to get less strength, but we could double our fracture toughness or our corrosion, stress corrosion cracking threshold. And with that, we made it into a leak before break. So when the crack went all the way through, it would just spray out the little stream of oil, and people get all oily, but they wouldn't get shrapnel going through them, okay? So you don't mind being as oily because you got slickers on anyway. But you expect them to fail, and if they don't, if your hardware doesn't fail on a regular basis in the America's Cup, you've made it too heavy. A little different philosophy, okay? It's actually one of the only industries I know where you design things so they're right on the edge of failure. But anyway, what else do I have on aluminum? Maybe that's most of it, I guess. To give you a feel for what we do in aluminum, the heat treatable alloys with their copper and their magnesium and their zinc, that's what gives them their strength by precipitation hardening, but it also decreases the corrosion resistance, okay? I taught you about scandium on baseball bats to increase or decrease the grain size. When we look at trying to get both toughness and strength, and I'm going to put up here, this is the old ratio analysis diagram that I had put up before, earlier in the semester. This is the one for steel, and this was developed out of the Liberty ships at the Naval Research Laboratory in the 50s and 60s, and it plots the toughness versus the tensile strength or yield strength of the material, and this is called the technological limit. This, at low strength steel, you can get very high toughness. As you go to higher and higher yield strengths, up to 300 KSI, your toughness goes down and your critical flaw size gets smaller and smaller. That's what these lines here. Critical section thickness is 2.5 inches. So you could build a pressure vessel out of anywhere, a steel with properties anywhere along this line, and it could be 2.5 inches thick, and it would leak before it breaks. You don't want a brittle fracture where it shatters like glass and sends shrapnel all around in a pressure vessel or a submarine, which is also an externally pressurized pressure vessel. But you get down here to 300 KSI steels, and your critical flaw size is 1/10 of an inch, okay? It turns out you'd like to have a ratio of toughness to yield strength, K squared over sigma, of 2.5 is kind of the difference between your plastic deformation region and your plane strain region. If you want to be in the elastic plastic region, which is where we can usually afford to design structures, you've got to have a fracture toughness squared over stress of 2.5, okay? Well, it turns out, actually it's fracture toughness over yield strength. So this 2.5 is kind of the ratio that we'd like to have. This is for aluminum, has 1/5 the fracture toughness. It has about 1/7 the strength, unless you go way out here, and it still has only 1/3 the strength. The critical flaw size, when you start getting into baseball bats or aluminum lithium alloys, you've got critical flaw sizes that are getting down to 1/10 or 2/10 of an inch, okay? Type of critical flaw size. critical depth of surface crack in inches, okay, depending on different ratios of these things, but without going through all that. So that's the ratio analysis diagram, and here's titanium. But I'm going to go back to the Ashby plot and just talk a little bit about structural materials in general. If this is the Ashby toughness versus strength, and for mechanical structural material, we're interested in toughness and strength as the two measures. Remember, strength is the force of fracture, toughness is the energy of fracture. If I have yield before fracture, it's going to deform before it shatters. If I have fracture before yield, I've got a brittle material that just shatters. It's going to be like a hand grenade and send shrapnel all around. If I'm looking at this K1C over sigma F constant of 2.5, it has this slope. There's another criteria for safe design of K squared over sigma. We won't worry about that one right now. But if here are the K1, oh, actually we will worry about it. K1C squared over sigma, oh, pi sigma squared. Okay, so this is the K1C over sigma. And that's actually, that is kind of the dimensionless number for the fundamental equation of fracture mechanics. But this 2.5, this is on a log scale on these dashed lines down here. This 2.5, I put a blue line in here. So this is the material, elastic plastic we'd like to design. This is brittle material. We got to be careful when we start using these types of materials on that side of the diagram. Well, let's look and see what we've got. Steels overlap, nickel overlap. Well, actually, nickel is mostly on that side. Titanium overlaps. All of your composites, graphite reinforced, carbon fiber reinforced, Kevlar reinforced. Aluminum alloys overlap. Copper alloys are always brittle. Magnesium alloys overlap. Okay, that's of the metals. If we look at woods, this is parallel to the grain. That's how we usually use a 2x4. Perpendicular to the grain, it's a brittle material. You would never put wood in that direction, okay, if you're trying to do a structural material. So wood is actually an anisotropic composite material. Plastic. And this 2.5 line splits right between them. Here are your ceramics, you know, rocks, pottery, most of your ceramics over here, even your high performance ceramics, and glasses are down here. So if we really look at structural materials, it's on this side of the line that we're usually working, okay? But we still have to be careful because this blue line cuts through most of these things. Most of these materials, well, this alloy is great and this alloy is lousy, and it's the same base system. Yes, is that a question? No, you just, okay. Sorry. No, you can twirl your pen. Okay. I just didn't know if you were raising your hand. In any case, I'm trying to bring it back to why we spent so much time talking about certain types of materials. So I'm pretty much done with aluminum, and I was going to go into magnesium, which I probably will. Remember, tomorrow we've got a guest lecturer. Adam Powell will be coming to talk about the company that he and Professor Paul, both of them used to be faculty members in this department in chemical metallurgy. But anyway, we do the periodic table. I will finish up on Friday. We have gone through, cross out iron. We've sort of done aluminum. We're going to do magnesium in a little bit. But as structural materials, we have not gotten very far, right? According to the periodic table. However, you can sort of cross out everything among the alkali earths. Hydrogen is not much of a structural material unless you're down at less than 20 degrees Kelvin. Lithium, these things are all too soft. I mean, you may not want to push on them with your finger because they will react with the moisture in your skin and cause sodium hydroxide and cause a burn, okay? But they're very soft materials, inherently soft. Francium, shoot, we can't even isolate it. The only time we've ever discovered it is we can see it in the spectra of some as an impurity and some other things. So it's sort of almost a non-existent material on Earth. It does exist on Earth, but only as an impurity in other things. You can't go buy a lump of francium, okay? Cesium, well, we use cesium for a few functional material things. Rubidium, shoot, we put that in. It concentrates in tobacco stalks, and they use tobacco stalks to make welding electrodes because they like the rubidium. Anything here is an easy electron donor, so we like to put sodium and potassium and rubidium and lithium into welding electrodes, fluxes, okay? But they're not structural materials. In this column, well, beryllium is a structural material. So let's talk about beryllium real quick. If you went back to Ashby's book and look at the price of beryllium, I haven't gone to look at it, but it's probably several $100,000 a ton. First of all, you get a lot of it per ton. It's a very light element. If you ever picked up a piece of beryllium, which I'm sure most of you haven't, it's like picking up a piece of paper. It's so light, okay? It has a very high melting point. Well, actually, it should be on here. Melting point of beryllium is 1560 centigrade. So it melts at a higher temperature than steel. What's it used for? At $400,000 a ton or whatever it costs. Spacecraft, that's the only structural application, but it's used all the time in spacecraft because it is so light and it's a very rigid material. It's relatively rigid. It has a fantastic strength to density, specific density or specific strength ratio. It's just way off the chart if you looked at one of these Ashby charts. But it's very expensive. Why is it expensive? Anybody know what the problem with beryllium is? Toxic. If you get any beryllium, pure beryllium powder, any compound in your lungs, and you are part of 10% of the population that has a genetic predisposition to berylliosis, you will get nodules form in your lungs that just start consuming your lungs, and you slowly die of suffocation. But the 90% of the people, it's not a problem. This was discovered right up here on the corner of Mass Ave, okay? Not where we have Building 35, but just on the corner, other side of the railroad tracks. I believe that's where it is. It could have been on this side of the railroad tracks, where the little bank kiosk is in the parking lot. But MIT, during the Manhattan Project in World War II, was working on beryllium for some nuclear warheads. It was sort of a new material. And there's some faculty members here working on the metallurgy of beryllium. And they had a little machine shop over there, and they were machining beryllium parts. And towards the end of World War II, beginning of just after the war, when they were working on nuclear materials, all of a sudden, a few of the machinists started dying of this lung disease. And they tracked it down and found out it was berylliosis, which had never been discovered before because it was a new material. But they showed through whatever, contaminating rats. It wasn't until years later I learned that, or they learned, and then I had to learn, that there's apparently a genetic predisposition. I think one of the students in the class did a little presentation on berylliosis once. And that may have been where I found out that it was only 10% of the population get it. But people are just deathly afraid of using beryllium. I remember I was cleaning out an old lab, Professor Grant's lab, or I had someone else cleaning it out when I was department head. And it's right around the corner from headquarters, and a young professor, actually Professor Shoes, professor at Northwestern, but he was a young professor here. He came in, he was in a fit because he had found a bottle of beryllium powder. And I went in, I said, David, it had probably been sitting there since 1946 or whatever. I said, it's got a cap on it. He says, it's dusty. I said, yeah, but that's dust from the air. I mean, it's had the cap on it for 20 years. This has been a lot, anyway. So, I went and picked it up. You picked it up, It's in a jar. I'm not going to dust it and throw it in the air and find out if I've got that genetic predisposition. But people are deathly afraid of beryllium. I mean, it's sort of beyond what they ought to be afraid of it. It has to be in a powder form. It can be beryllium chloride, beryllium oxide, beryllium metal. It gets inside your lungs and you're part of that 10% of the population. You've got serious problems. So it's toxic. But it's also expensive to manufacture, in part because it's toxic, so they have to have all these controls so the people manufacturing don't get berylliosis. That's one of the reasons it's expensive. But it has one application, which I keep on thinking I ought to buy one of these tools and bring in. It's called non-sparking tools. You can take copper alloys and you can give them 180 or 200 KSI strength by a precipitation heat treatment by copper beryllium. So you can make a copper 2 or 3% beryllium alloy, heat treat it, and end up with a copper alloy that's as strong as some of your strongest steels. Okay? And they use it in mines for non-sparking equipment. If you're in a mine, you've seen steel shovels or other tools get a spark when you hit them, right? It's not a good thing in a mine full of methane. Okay? You could have a gaboom, okay? So in mines, they actually use high thermal conductivity tools, which copper is a high thermal conductivity material, and you make beryllium copper, you get a hard tool that's non-sparking. You can go with copper beryllium alloy hammers, and you can bang them against a copper beryllium nail or pick or something, and it won't spark. You can do it all day long. There's enough heat transfer that when the frictional heating goes in there, it carries the heat away faster than the ability to generate temperatures sufficient to cause sparking. That's not true in steel, and you'd love to do it in aluminum because it'd be cheaper than copper beryllium, but aluminum just it's got good thermal conductivity, but you can't get 200 KSI strength in aluminum in any case. So that's beryllium. We just covered beryllium. Okay, check that one off. So let's go down the periodic table here. But I'm going to skip magnesium for just a second. Calcium. We've actually talked about that. How do we talk about it? It's used in larger quantities than steel. It's called Portland cement. Okay, I gave you the formula. You take calcium carbonate, called limestone. All these little sea critters gave their lives and deposited themselves at the bottom of the ocean over millions of years, and earthquakes and stuff brought them to the top, and we go mine it, turn it into powder, spread it on our lawns to get rid of the acid rain. But we also can take it, put it in a kiln, and drive off at 1,000 degrees centigrade the CO2 and end up with calcium oxide, also known as burnt lime. Okay? And then you take that and you mix it with water and you get calcium hydroxide. Now, it's not always calcium, pure calcium limestone. Some of those little critters had magnesium in them. It might be, I think dolomite is 50% calcium and 50% magnesium carbonate. And so some of your Portland cement is a calcium magnesium alloy, but we actually do use calcium as a structural material, and it's called Portland cement. It's used in a larger quantity than iron, so we covered that. Okay. Magnesium. Well, let me finish up these. Strontium and barium start to get very soft. Radium is actually, some of that forms as radium's radioactive, isn't it? Some of it's got a fair number of radioactive species. Yeah. They also used to drink it back in the 1920s. Have you ever heard about that? When radioactivity was sort of new, people thought they'd make these radium cocktails, and they thought that by drinking it would make them feel better, sort of like 5-hour energy. Okay? But it was very expensive. And then people found that the longer they drank it, they started having other effects. And they decided maybe it was expensive. But there's one guy who was very wealthy, and he, to his dying day, would drink a glass of radium every day. And it turns out his dying day didn't take too many months, because his bones started decalcifying, and he started turning into just sort of like an amoeba and stuff. No structure. So maybe we can call this an anti-structural material. But anyway, this is in the 1920s. So these things don't really count. But magnesium, okay? Magnesium does count for something, okay? Let's talk about magnesium a little bit. Magnesium, let's talk about the quantities of magnesium that are used in the world. So here's shipments of magnesium from 83 to 88. It didn't really matter too much. They didn't change dramatically. The 28,000 tons, metric tons, was used for die castings, gravity, and then 37,000 tons for gravity and wrought products. Only 7,000 of the 37,000 is wrought products. Wrought meaning sheet or rod or something. Someone was talking to someone, they wanted to use magnesium, or they wanted to deform magnesium, and I said, it's not easy. Well, this is an example. It's not easy. You have to heat it up, you have to do it warm. It's a hexagonal close-packed metal. Can be made into sheet, but you have to really know what you're doing. Okay? Mostly we use it as casting. That's structural. Non-structural, the bulk of magnesium is used to make the 6000 series or 7000 series aluminum alloys. In fact, about half of all the magnesium made goes into alloying for aluminum. Okay? Desulfurization, that goes into steel to get the sulfur out. Okay? You just form manganese sulfide. Nodular iron, you can make cast iron and you can change the graphite morphology and call it ductile iron. So that's actually a growing market segment. You can see it growing fairly dramatically up until even beyond 87. Metal reduction, magnesium is so reactive, you can make magnesium metal and then you can react it with some chloride or fluoride of something else, like tantalum chloride, and you could make tantalum metal, okay, out of magnesium metal and tantalum chloride. And they in fact do that. All your tantalum capacitors are made by magnesium reduction of tantalum chloride or tantalum fluoride. So metal reduction. Chemical uses of magnesium, electrochemicals. If you own a hot water heater or your parents own a hot water heater, it probably has a magnesium anode, okay, going down the center of it. A sacrificial electrochemical anode that will corrode, just like zinc on galvanized steel becomes the anode that corrodes and cathodically protects the steel in a hot water tank to protect the copper, the brass, the steel, anything you got that the water's coming in contact with in the hot water tank. Use magnesium as the sacrificial anode. Yes? They use aluminum. Yeah. Magnesium is better. The problem with aluminum, if you have certain ions in your water, the aluminum can form a passive scale on the surface. And all of a sudden the aluminum becomes non-anodic, becomes cathodic. Aluminum is sometimes called amphoteric, which means it can switch its polarity in the galvanic series. So aluminum in proper conditioned waters is fine as an anode material, but magnesium is better because if you look at the galvanic series, all the way over here, the most reactive is magnesium. And all the way over here, the least reactive is graphite. And it's like an extra ½ volt you get out of magnesium compared to zinc. I mean, magnesium has really it's really the most electroactive of our common, sacrificial anodes. And actually two structural applications. The U.S. Navy out in Port Hueneme, California, where they have a diving school, they developed about 30 or 40 years ago. People were interested. I mentioned these aluminum silicon carbide composites. People in around 1980 or the 70s and 80s were very interested in these ceramic metal composites. And so the Navy was trying to make lightweight magnesium composites that had silicon carbide or graphite or whatever in them. And I remember Professor Latanason, who worked on corrosion here, he was working on some of these things, and he found that if he tried to polish them to make a metallographic sample, they would corrode faster than he could polish. So they had to polish them in an oil rather than a water system, because you got graphite and you got magnesium. And those are the two far ends on the galvanic series. It would corrode so fast. But the Navy said, it corrodes fast. We will use that property of rapid corrosion of this composite. And they found two uses. One was you could take this alloy, this composite, and in a plastic bag down, the divers could take it down. And when they're doing salvage operations, one of the things you sometimes do is build a great big balloon and then fill it with gas to lift the salvage to the surface. Just a great big bubble. Well, they didn't have to pump gas down, a couple hundred feet. They could just break open this thing and it would corrode and generate hydrogen gas. You just had to be careful when it got to the surface that you somehow attached it before and dissipated the hydrogen before you blew it up. But in any case, they used it as a salvage material. The other thing, it would corrode so fast that when divers were diving in cold water, they could strap it in these plastic things, and if they got cold, they could just pierce the plastic and it would corrode and generate enough heat to keep them warm. Okay, so, but you have to understand, one of the Achilles heels of, they only made 200,000 tons in 1983, they were making 250,000 tons in 1988. 250,000 tons? Well, aluminum's like 40 million tons, right? And steel's 1 billion tons, okay? So yes, magnesium is one of our structural materials. It has several Achilles heels. One is the fact that it corrodes. It's a great corroding material. Actually, the Navy called these super corroding alloys, okay? But it has other problems, but in addition to corrosion. One problem is that it will burn if you get to certain temperatures. And if you want to see this, you go to New York City. You go to one of the poor areas of town where they torch cars on the sidewalk to get the insurance money, okay? Your car's a junker, but it's got mag wheels, okay? So you torch it, and the magnesium, throw some gasoline on a car and on some magnesium, and the fire will get hot enough, the magnesium will ignite, and you get a really hot fire at that point. Burns at about 4,000 degrees. Magnesium is used in flares, it's used in fireworks, in powdered form, and gives bright white lights, okay? So it burns because it's so reactive. It also, you develop residual stresses. So you try to weld it, and the humidity in the air will almost crack it right behind the weld. I mean, not quite that fast. But you come back 2 days later after having fusion welded magnesium alloys, if you haven't stress relieved it, just the humidity in the air will cause stress corrosion cracking, okay? So that's why most things are castings, because castings don't have residual stresses. And most of the magnesium that goes on automobiles used to be in the wheels, and they would just paint those for corrosion resistance. But now it's kind of going underneath the dashboard in places like that. Very specialized applications. It does come into play in some things like the Black Hawk helicopter. I mean, here's an old article about the Black Hawk helicopter and the use of high performance magnesium. The US government is constantly spending tens of millions of dollars every year to try to develop a magnesium, low-cost magnesium market, because they say, oh, we can build lightweight automobiles. Well, you can't roll sheet very easily, and they sort of make automobiles out of sheet. You can make castings, but I have yet to figure out why they do all this. Tomorrow when Adam Powell comes in, he will tell you that one of the first things they did was, with his technology, was to make magnesium, because they could get several $million from the US government to make low-cost magnesium. Magnesium costs about twice as much as aluminum. In terms of energy costs, it really shouldn't cost any more. There's a guy, Joel Clark's first doctoral student here in the mid-70s, did a thesis on the magnesium business and the cost of magnesium, and he didn't say it as directly in his thesis because he could have been sued probably, but his basic conclusion was that after World War II, Dow Chemical, which has sort of a monopoly on magnesium production, of this 250,000 tons, they may make 200,000 tons. They got a near monopoly on this stuff. They, according to Dr. Kenny, it appears that you can track the price from 1946 all the way up to 1975, and the magnesium and aluminum prices tracked perfectly with one another. And you can do statistics and correlation coefficients. There is no economic reason for that to be true other than an illegal cartel, okay? But Americans don't do that, okay? So obviously it's not true, right?